yeah, you work at the different side, but both at Software Center, University, and at Chalmers.
Yes.
I guess you represent all of them. So we're going to hear about machine learning, and then in particular in the automotive development. So,
thank you very much.
The scene is yours.
So first of all, thank you for inviting me. I will show you some of the opportunities and challenges with machine learning in developing software. So it's not only about image recognition, although I'll get a lot of examples of that. So first of all, I would like to introduce the concept of what is machine learning in software engineering. Why am I so excited about that? I'll show you some of the opportunities and challenges of that. I'll show you in particular two areas. One is classifying source code, which you can probably know from areas like MISRA analysis or safety analysis of your systems, and also defect clustering to find out which defects are essentially problematic or not. So, why this is a paradigm shift for software engineering? Well, first of all, think about it in this way. I mean, when we constructed systems before, we were very sure about what's coming in and what's coming out, the input and output. We used to develop systems based on control loops, Simulink models, and similar formulas. But that may no longer be the case. If you look at this example, I mean, that number in between that I crossed in the red circle, who said really that it's a 5? I mean, it's an arbitrary choice of me as a designer to label that particular number as 5. But that causes a challenge in machine learning or in automotive software development. And the challenge is because we suddenly have to move from knowing that it's a number 5 to actually working with probabilities. And we also have to think about this, that in machine learning world, not always am I as a human the right oracle for the machine. Maybe sometimes, in some cases, machine can be much better than I am, which causes a lot of challenges on that. So one of the challenges that I will discuss later on is this working with probabilities, that we no longer know for sure what is what in the algorithms inside our systems. What also I will talk about is that the challenge of using machine learning is no longer in actually designing the system. It's the designing of the training set. I will show you a few examples of why this designing of the training set is so important and why machine learning has a different potential that we as humans have. I'll use a very simple example of decision trees which can actually, well, where we can actually see how the algorithm is classifying instances. When we can look inside that algorithm and we could actually, if we wanted to, devise test cases that could work with coverage-based metrics to show that. And then why I'm excited about this is that we no longer work with testing. We work with validation. We work with statistics. We work with false positives and false negatives and true positives and true negatives and all kinds of things. So we move in from a spectrum of actually right and wrong and oracles to working with probabilities, with statistics, which is very, very different in many cases. So, first of all, let me introduce you to the machine learning by example. Let's look at how we assure safety of software in some cases when we look at the MISRA coding guidelines. Many of you know that, right? It's basically on top of C++ standards saying what we can and cannot do with C and C++. So imagine we need to find those MISRA violations in a code. And that code base is usually quite big. It could be like 100 million lines of code for an automotive system. We don't really know exactly the grammar of the programming language, because C, even if it's one language, it could be in different versions. And if we know the standard, maybe we not always can compile the code because either we don't have all the libraries or maybe the code is incomplete yet. Or we cannot really show all kinds of examples manually because they are just too difficult to create. And those of you who know MISRA rules, you know that the examples are really tricky. And even if the examples are simple, finding whether a piece of code follows them or follows a guideline or not, it may not be that tricky. And of course, there are standard solutions. There are MISRA C compliance checkers. But even they, those of you who've used that, even they provide quite many false positives and false negatives. We cannot really 100% be sure that they provide us with the right example. So is there a better way? Now, look at it like this. How about instead of writing a rule, what is right and what is wrong, we could show the example of a coding violation to a program, and then the program would come up with a rule. What's cool about this approach is that we no longer have to understand how to write this program. We only have to understand what kind of things are right and wrong. We can provide more examples. We can look at the output, and we can see what is good and what is bad. So in this case, I give an example of a source code, and I mark with red the problems that I don't like to see in my code. Then I let the decision tree to come up with a set of conditions fully automatically, and I could apply that to the whole code base and find those kind of patterns in the entire code. So where's the magic? Well, the magic is in the way how machine learning translates a program or anything it sees into its internal representation. So it takes each line of code and it collects a number of features. And then it tells me if it should be counted or it should be ignored in a specific case. Now, as you see here, this particular tricky part is actually demonstrating how machine learning sees my objects. So whether that is line of code, or whether that is a picture, an algorithm doesn't see this the same way as I do. What it means? Well, it means that something that sometimes, for instance, if I see this line and this line, for me, they may be completely different. But because of the internal representation of those lines, they could be completely identical for the machine learning. And that means that sometimes when we have a picture of a dog, for some dogs, they will be recognized as cats. Just because internally, for the algorithm, the dogs can look exactly like a cat. Could be because of noise, but could also be because of this. And I'll come back to that challenge later on. So this internal representation is actually quite interesting because it takes all these features and attributes. And the question is, if we work with images, we usually work with pictures. But if we don't work with images, how many of those features or how many of these attributes do we need in order to be able to recognize objects correctly? So maybe my complexity of writing the code is not really in finding this, because this can be done automatically. But the complexity has shifted to the way how I design my vector, how I teach my machine learning. And of course, the more features I have, the more mathematical problems. I mean, I could have theoretically infinitely large feature vector that will classify all objects independently. But first of all, it's impractical. And second of all, I come up with a lot of bad mathematical properties like correlations or dense matrices and so on, which are very, very problematic for many of the algorithms, right? So I need to have as little as possible for that. And the challenge for me now as a software engineer is no longer to work with this, but to work with that. How should I characterize my objects for the machine learning so that I get the best results possible on it? And in order to do that, I need to work with the structure of my program. So now, as you see, I only work with the code. The abilities that I have for now, compared to, for instance, static analysis, is that I no longer really need to understand if it's a Java code or if it's a C code or C++ code or any other programming language. In a best case scenario, I could actually show examples of a code in Java and find the violations in C code, because they are quite similar. I only understand lines. What else I could do? I could actually have a number of test cases that could look at this algorithm and test all possible execution paths, right? So I could get 100% coverage by looking at this. And I could actually understand where I have my problems, where my violations could slip. Where is the cases which I actually ignore when I shouldn't ignore, and provide counterexamples. So compared to the neural network approaches, where we have black box, the white box methods allow us to understand how the software sees my units, my entities, my objects, and how it classifies them, which gives me a lot of possibilities to tune that and to train those models. So I could actually apply that to a new code base, find out which lines violate a specific rule, and also get the rule which they violate. So I could know exactly how they work. I could backtrace that. Something that is tricky for black box algorithms is quite simple for this. So how does it work in practice? Well, we applied that on a large code base. We look at this rule, which is very simple for a human eye, but it's not as simple for the automatic parsers to find. So how do we do? We try to find examples of variables which are declared, two variables per one line of code, or more variables, several, 20, 50, all kinds of cases. Now this example is extremely simple. So when you see this example, of course, you can write a parser for that. But how many data types do we have in C? Well, infinitely many, right? We have all the built-in, but also we have all the ones that we create. And how we create them, how we instantiate them. Not in constructors, but in functions, local, global, and so on and so on. So we did an experiment. We ran that on an industrial case. We started with the very first run when we only took the example that you show on the previous slide. So basically 3 lines of code, which for a neural network or any black box algorithm is basically insufficient. And we applied that on the code. We got some results. We look at the results and say, well, that's complete rubbish. We need to take a lot of things and put them as false positives, as false negatives. So basically, we wanted to add more examples. So we added more examples. So in the second trial, as you see, we had about 120 different lines as examples. Again, not a lot of good results. Almost 0 correctly classified instances. So we did it again. And when we did it again, added roughly 100 lines of code, 100 lines of examples more, you see that we started to recognize many more violations in the code. But as you see, accuracy was only 15% or 18%. We did it again. The accuracy dropped. Why did it drop? Because we actually added lines that for the machine learning were identical, and we added them to 2 different classes. One that contained violation and the other one that didn't. So even if we could recognize the difference, the algorithm couldn't see the difference between those 2. So it got confused. So we removed some of those lines, added 3 more examples, and then suddenly, with roughly 260 lines of code, we could find 70%, we could find almost 70% of the violations in the code. Or 70% of the violations we found were actually correct. What does that mean? If you look at how many times we have to do it, we had to do it 1, 2, 3, 4, 5 times. 5 iterations, looking at the code. Few seconds of execution. We could get, if we find 1,000 lines of violations, 700 lines of those were correct and 300 were not correct. It's not safety critical. For safety critical, that will be completely unacceptable. But for finding violations, it's a pretty good result. I mean, compare that we used 3 million lines of code product. So instead of reading 3 million lines of code, we provided 260 lines of examples. And already got quite a lot of good results, right? So, based on those experiments, we could see that for different rules, we could very quickly get very good results for Whitebox machine learning systems. It takes about 20 minutes for those algorithms to go through the code, make a big feature vector out of that, classify that, and spit out the results, which is quite quick. Again, it's not accurate to 100%. It's only 70% accurate, but it's pretty good. It still saves a lot of time. We even tried the same approach for looking at the defects. So if we have a number of defects that are coming in your development project, you would like to quickly know which ones should we prioritize. So we would like to have the same kind of decision tree. We did this, exactly the same approach, exactly the same algorithm, and we look at the number of defects. So we look at the big defect database from industry. And what would we do? Well, we try to predict whether a bug should be fixed in a specific release or not. It's not a safety critical system again, but it's something that gives you a very good example of what we could do with machine learning. So how did we do that? Well, we looked at the exactly the same thing as previously. We look at the defect database, the description. What does it really say? Well, we took the defect, and we found that out of about 50 different features, only 3 are so important that give us good result. So we only need to know 3 things when a defect arrives in order to be able to say whether we should fix it or not. And we did it for different types of defects. And these are just examples of that, right? Sometimes we need 4. We also could find out how good the rules are in terms of false positives and the other issues. So how do we do that? We again got exactly the same type of tree. So basically a huge if or switch statement that we could basically test. So we could write test cases to run through all of those execution paths and find out what is going on. We could even find out whether they are doing things right or wrong. Both build statistics, but also look at the pure testing. So we could bring in those argumentation to coverage-based decision criteria. What we could do is that we could distinguish all kinds of defects, for example, severity A defects from other kinds of defects, right? So those that we should fix quickly or not. Those are difficult from those that are not. We look at those feature vectors. We look at how many things we could do. We also found that out of quite many features, 3 or 4 that were directly available were the best ones to classify. Again, they are not 100% correct always, but they give a quick and dirty understanding. So instead of a human being reading the defect report, one can just run the algorithm and get a very, very quick classification that can be rejected or validated. One of my students actually worked on using neural network to find out whether neural networks are very good in predicting a distance of a vehicle, electrical vehicle. So he has run a project together with his industrial partner, and Eric was trying to predict the next change in the vehicle speed in an electrical vehicle. He used a lot of vehicle logs. The vehicle log look like this. So it's basically this logs the change in the speed of a vehicle if it's more than 5 kilometers per hour. So if it's going up plus minus 4, it doesn't record that. But if it's changing plus minus 5, it records that. So it's a bit dragged, right? It's not a smooth line. But one could predict that. And why do we want to predict that? Well, we would like to know exactly how much distance can we drive on an electrical battery. What he did, he applied those kind of methods. And the difference between the upper picture and the lower picture is that in the upper picture, Eric has applied a very trivial algorithm. So basically, his algorithm say the speed in the next second is going to be exactly the same kind of speed as for this second. On the lower part, he applied a very complex neural network. And as you see, even a very complex network sometimes is completely wrong, right? Look at this one. I mean, here the network predicted something that never really happened. And the trivial algorithm, of course, is extremely trivial. It's very easy to backtrack. It's not perfect, but it's easy to understand. If we look at the average error of the configurations, the blue lines are the configurations which are, it's called 0 here and t there, which are trivial configurations. So basically saying that the speed of the vehicle is going to be the same in the next second, is going to be exactly the same as in the current second. And as you see, it's not that bad. So simple algorithms sometimes actually outrun the more complex algorithms in many cases. So, having said that, what are the challenges? Why can't we just apply machine learning completely? Well, one of the challenges, and that is a big challenge today in the automotive industry, is the fact that this is how a car's electrical system looks like. It's a lot of small computers. There may be a few big computers, but there is a lot of small computers. What does that mean? That means that the data we have is not just one big feature vector. It's a lot of small ones. What else does it mean? That means that there is no single format, because the computers log things in different ways. Some computers log things based on the speed, sometimes log things based on time, some computers log them in a different way. Which means it's very difficult to put them together in one big file to apply machine learning. What it also means that it's extremely difficult to have multiple keys, or it's easy to have multiple keys, but it's extremely difficult to have single timestamp. Simply because those computers need a bit of time to communicate. They need to send signals. So not always the same second the time is not always the same. So how do we put that together? So, well, things that are going on in the automotive industry is that we try to put in together bigger and bigger computational units, more centralized, that will enable machine learning in a completely different way. It will enable us to have one data set that is integrated from many sensors because of fixing a lot of those issues. We could have single format, we could have one key, one timestamp. So basically what we could do is we could just have the methods I showed you very easily implemented on a single CPU or ECU in a car. Meaning that the car will be smarter and a bit more safer because of that. There will be much less effort in integrating the data. But that's still not there. Another challenge that I mentioned is related to this. Sometimes in the data set, the way machine learning sees the data and the way I see the data are very different ways. Meaning that I could actually introduce inconsistency that will stop or prevent the algorithm from learning anything. Now you know this kind of optical illusion, right? Is that a vase or is that a person? Now that's a trivial example, right? And we can see that. But if we provide this to a neural network or any machine learning algorithm, it will never learn. Because it will never be able to identify what is what. There is an inconsistency in the data set. And as I showed you on the example with a line of code, it's extremely easy to introduce that inconsistency just because of the complexity of how machine learning sees my objects. What the computer sees is not the same what I see. Those two things could be completely different for us. So for me, something could be extremely easy to spot and show the difference, but for an algorithm, those two things may be indistinguishable. Meaning that I need to have tools to be able to remove all the problems with the data. So increase data quality. So the challenge with machine learning, another challenge with machine learning is that we no longer have to work with so much complexity of the algorithm as much as with complexity of the data and quality of the data. Because if we cannot if we cannot recognize problems at the very low level with sensors and cameras and radars, what happens is that we get a lot of uncertainty the more complex algorithms we use. So if we don't know if it's a snow or if it's a distortion in the camera, we need to work with some sort of probability later on saying that it's either a snow or it's a distortion or it's a broken camera. And we need to distinguish those two cases. And if we need to distinguish those two cases at this level, then maybe the architecture needs to distinguish all four cases. You know, it could be a wrong camera and distortion and snow. It could be snow and no wrong camera, and so no broken camera, and so on and so on. And then we have to deal with a lot of different actions on that. So the quality of the data is really, really important for that. Without having checks on the quality of data, and today's standards like ISO 25012 or 25024, they don't recognize that problems at all. They basically assume that consistency is there. And for machine learning, that's a showstopper. And finally, the last problem I would like to bring up is to look at the validation of that. And we saw a few talks about neural networks and how we could work with safety analysis of those. But basically what we can say is that today's coverage-based criteria that are used in standards like ISO 26262 are completely useless for machine learning, because they don't really mean a lot. Instead of talking about coverage-based criteria on the code or the algorithm, we should be talking about coverage-based criteria on the learning set. What is it that we provide to the machine to actually learn the patterns, and what kind of patterns we learn? So, to sum up, I think that today, with the introduction of much more complex algorithms in machine learning and the ability of using that in many different cases, automotive software engineering will change. Many of the automotive software companies are moving over from waterfall and V model to more agile. What that means that the code, for example, is no longer developed in big chunks. There are snippets of code that are being reviewed. There are tools like Get or Git that provide just small pieces of code that one could review, that one could validate, which means that static analysis tools will no longer be able to be applied. Maybe we won't have a source code that we can compile later on. So we have a lot of opportunities with machine learning to basically look at all kinds of optimizations in software engineering. But there are, of course, challenges. And the challenges are both on the side of how we apply them, but also how we work with machine learning. That we, as software designers, need to understand how that magic inside an algorithm actually works. That it's not always just small numbers in a neural network, but it's a feature vector. And what does that feature vector really mean? How can we distinguish objects that are very, very close to each other? How do we know that the neural network recognizes a cat as a cat and a dog as a dog? How can we create data set that will make sure that the neural network will not confuse one with the other, or with even simple algorithms? And there, I think that a lot of work on education and competence development in that area is needed to work with simpler algorithms and to understand how they really work from the perspective of data analysis, not from the perspective of how we write a Python code or how do we use TensorFlow. I think that's a critical issue for the next few years in automotive and embedded software development. And with that, I would like to thank you for listening to me. If you have any questions, I'll be super happy to answer them. Thanks. I can hear it. So I don't have the answer how do we address that, but I fully agree with you that yes, we should be thinking more about the models and the data sets rather than the the paths and execution paths in the code. Yes. Okay. Thank you very much.